When we start out learning FEA, we often use classical hand calculations as a method of gaining confidence in how we set up our FEA analysis. And so a classical problem would be a simply supported beam, in this case a wide flange beam, commonly referred to as an I-beam, but the standard name is a W wide flange beam. And in this case the W10 by 100, the 10 is the nominal width of the beam, so approximately 10 inches wide, and then 100 pounds per foot, so W10 by 100. And let's look at how to set this up. Now when we go in to do an FEA analysis, we sometimes find that our hand calculations were a simplified representation to make it possible or practical to do the hand calculation. For this lab I will set it up as units inches, and I want my results to be shown in inches as well, so I'll go to preferences and I'll go to simulation and make sure that my results are set to English units. And then I'm going to start a new sketch on the YZ plane. Do a new sketch. I'm going to start out with a center point rectangle at the origin. And then I'm going to do two rectangles, one above and one below the previous rectangle. And then I'll do a midpoint constraint between this line, and a midpoint between this line and this line. I'll then put some dimensions on here. And before I do that, let's make some of this geometry equal. So I'm going to make this line equal to this one, and this one equal to this one. And then I'll put some dimensions on here. And this one I want to be 10.3. And for the overall height from here down to the bottom, I want that to be 11. And then when I did that, it took this end of the rectangle below, and I want that actually to be on this side of it, so make sure you have it on towards the inside. And I'll dimension this distance from here to here as 1.12. I'll dimension this distance from here to here as 0.68. And our geometry turns black. It's all fully defined. And so now I'm going to extrude this. And so I will go to the solids tools, and I'll do extrude, and I'll select all three of these rectangles, and I'm going to extrude that out a distance of 480 inches. Or 40 feet. Alright, then I'm going to put a fillet in these corners, and that fillet radius is 0.5. Select that edge, right click and do fillet, and my fillet radius will be 0.5. And I'll also control select this edge, control select this edge, and I'll also select this edge. Alright, so I have my half-inch fillet in those corners. I'm going to check my material, and so I will go to the properties, and I see the physical material is steel. I want to make sure that I'm saving this in my DSG 326 folder, and I'll save this as Lab 6, Gravity and Weight. Alright, so I have a 40-foot long beam. I want to reproduce some classical hand calculations on this beam, and I'll go to the simulation tab. We're going to do a static stress, and then for the first analysis that I'm going to do, I'm going to constrain the end of this beam right here and on the other end. For the second analysis I'm going to represent this sitting on an 8-inch block wall, and then for the third analysis I'm going to attach it to a block wall. So let's copy these studies. And when I copy the study, I don't want to merely clone this study. I'm going to go to the simplify, and I will then select create a new simulation model, and I will finish that and tell it I want to do a static stress analysis. Okay, so I have simulation model 1, simulation model 2. Let's go back and make simulation model 1 active, and I'm going to put my structural constraints on, and I will select this edge right here. I'll do a fixed constraint on this edge, and also do a fixed constraint on the edge over here. Now that doesn't allow these ends to move. And then for our load, I'm going to only define gravity. So I will turn gravity on, make sure that it's pointing down. So the only load will be the weight of the beam itself. I will do a mesh. Now when we have a really long part like this, it could take a long time to do a mesh calculation. So we could also use beam elements, which we will see in a few minutes. It took a really long time to do that mesh, so we might find that it's not worthwhile to increase the density of the mesh, but nevertheless I'm going to increase the density. So I edited the mesh and changed the average element size to 5%, and it took about twice as long to mesh the object. So it may not be worthwhile, given the difference in results, to increase the mesh density. We'll then run the simulation. Now we haven't set up the simulation model 2 yet. That's why it's showing it's not ready to run. We'll set that up in a few minutes. And I'm going to run this one locally. The analysis is finished. We see that we have a safety factor of 6.45, a minimum safety factor. If I go to the stress, we see the areas where the stress is higher, where we have the fixed constraint here and the fixed constraint on this end. And if we then go to the displacement, we see we have a displacement of about 0.17, and that is the bending of the beam under its own weight only. So we haven't put an additional load on here. We have only the weight of the beam. Remember that this is an exaggerated deformation. If we put it on the actual deformation, compared to a 40-foot length, we can barely see that deformation. If we want to animate that bending, we can click on animate and play, and we see how the center of the part bends towards the inside. Now notice here on the ends that it's rotating around this point towards the inside, and the same on the other side. In this example, we put the constraints on this very edge, but in the real world, it's not likely that we're going to have a situation where we have a beam constrained just to the edge. But that is a simplification that represents our classical hand calculation, or one method of our hand calculation. Let's look at some other results where it isn't fixed on both ends. I'm going to make simulation model 2 active, and then I'm going to split the face on this end and on the other end as though this was sitting on an 8-inch block wall. And so I'll do simplify, and I'm going to then create a sketch on this face, and I'll draw a rectangle from this corner over to this edge, and then I'll dimension that rectangle as 8 inches. And it's showing my units here in millimeters, so I come up here and change my units for this analysis as well. Alright, so I have an 8-inch on this end, and I'm going to do the same thing on the other end. So I'll draw a rectangle from this corner over to this edge, and I can either do equal or put a dimension on there again. Let's go ahead and do the equal. This line is equal to this line on this end, so if I decide I want to change that, I could change those both at the same time. Alright, then I'm going to go to split, so I'll do modify split. I want to split that face, and I'll select this face as the face I want to split. For the splitting tool, I'll use this rectangle, and I'll say OK to that. So we split this end. Now I like to make this a different color so that I can clearly see it, and so I'm going to right click and go to the appearance of that face, and I'm going to select some color, and then I want to put that appearance only on that face. So I'll select face and drag and drop that onto that face, and then I'm going to do the same thing on the other side. So I need to make that sketch visible again. Turn on the visibility of the sketch. I will do split again, and I want to split this face with the rectangle on this end, and I want to change the appearance of that end as well. So I have this face split from this face. I'll go to the appearance of that face, select faces, drag and drop this appearance onto that face. Alright, so now I have the 8-inch block on this end and the 8-inch block on that end. I'm then going to clone this study, and so on simulation model 2 I'm going to clone this study. Once I have split my faces, I'll finish simplify. So now we have two simulation models. I have the simulation model 1 that we ran first without the split ends. Then I'll make active simulation model 2, and then I want to run simulation model 2 several different ways. So I'm going to go to the study 1 under simulation model 2, and I'm going to clone that study, and then I'm going to clone it a second time. So I'll go to study number 1 and I'll clone it again. Okay, so it's under simulation model 2. I have 3 studies, study 1, 2, and 3. Let's make study 1 active, and I will generate the mesh. Now I probably should have done this before I cloned the studies. It takes so long to mesh this long part that I'm just going to leave it at the coarser mesh. And then for our loads, we'll define gravity. So I turn gravity on, and then I need to apply my constraints on this part, and so I'm going to place a frictionless constraint on this end, and I'll also place a frictionless constraint on this end. So this part is free to slide back and forth on top of the 8-inch block wall. So 8-inch block wall on this side, 8-inch block wall on this side, and the beam is just setting on those two block walls. I'll then run my simulation. So I'm doing model 2, study number 1, and then we'll set up study number 2 and 3 on model 2 here in a moment. Now notice that our part, if I go to the displacement, moved in an unexpected way. So we had it sitting on top of a block wall, but it has slid sideways, and that's not what we expected. In fact, it might give you an error. The displacement is 847 inches, and so it should have given us an error saying there was an excessive displacement. So let's look at how to fix that issue. So we're doing static analysis, and a body moving 847 inches is not static analysis. So we'll go to the Manage tab, and I'll go to Settings, and on the settings I'm going to check mark this Remove Rigid Body Modes. When you see this word mode, think vibration or motion, and so we want to remove the rigid body motion, and I'll select OK to that, and then I'll run the simulation again. After running the simulation again, it returns a displacement of 0, and so this is a bug in Fusion 360. We should still get the weight of the beam causing the beam to sag down. Let's look at doing an alternative study. So I'm going to go to study number 2, and this time I'm going to do a fixed constraint on one end, and then I'll do the frictionless constraint on the other end, and then I'll run study number 2 of simulation model number 2. I need to define the load, turn gravity on, so we have our fixed constraint, our frictionless constraint, we have gravity. We'll run the simulation on study number 2 of simulation model number 2. Our simulation is completed. I'm going to put it on adjusted times 0.5. Remember, actual is only moving about 0.17. So I will check my placement, and on this one we have a displacement of about 0.1. So our displacement has, with this end fixed and this end resting on top of the 8-inch block wall. In this example, I'm going to reproduce the lab in Autodesk Inventor. So I'll start a new part file, and I'll start a new sketch on the XY plane. Then I'll draw a line going from the origin over 480 inches. I will save this file, and I'm going to call it Lab 6 Skeleton. And then I will start a new assembly, and I will place the skeleton file into the assembly. I'll right click, place grounded at origin, save my assembly, and then I'm going to go to the Design tab, and if your content center is on Vault, you will first need to log into Vault, and I'll go to Insert Frame Member. I'm going to do ANSI Standard, and I will select a wide flange beam. And for the size of it, I'm going to do a W10 by 100. We'll leave the material as mild steel, or we could set it the same properties that we had in Fusion 360 was steel. I'll select this skeleton, and then I'll say OK and accept the file, ANSI W10 by 100. Turn off the visibility of the skeleton. All right, we'll look at several different ways of doing this analysis. The first method I'm going to do is a simple frame analysis. So I will create a simulation, and then I'll put a fixed constraint on this end, and I'll do floating. I'll then run the simulation. Okay, with that we get similar results in the same ballpark, 0.126 thousandths of an inch of displacement, but we didn't have to mesh the part. So using beam elements, the analysis ran much faster than with a tetrahedral mesh. But let's look at running this with the tetrahedral mesh. So I'm going to right click on the part and open the part itself. With Y pointing up and Z pointing over to the right, I'm going to call this the bottom of the part. So I'll do a new sketch on the bottom and do the split a little bit differently to simplify the procedure. I'm going to do a rectangle about like that, and then I'll dimension from this end over to here as the 8 inches, and then I'll do the same thing on this end from here over to here, and I'll do that equal to this dimension. Okay, and then we could constrain the height of this, but it really doesn't matter. I'll then do my split, and I'll select that rectangle, and I want to split this face. So we could do that with one operation instead of two operations by doing that rectangle. I like to change the properties of the appearance of that face, and so I'm going to make that, say, a beige on that end, and if I pick up that color with the eyedropper, I can drop that same color over here. Okay, so now I can keep track of where the bottom of my part is. I don't see that feature that I just created unless I go over here to modeling, and so now we see that split face that we just put on the bottom of the part. I'll then run a tetrahedron analysis on this, so I'll go to stress analysis, I'll create a study. And for the initial study, I don't want to have the split face on the ends here, so I'm going to ban this node, and on the split face I'm going to exclude that from the study. Right, then we'll do a fixed constraint at this end, and I'll also do a fixed constraint at the other end. We'll define gravity. I will select the top of the part. I want gravity perpendicular to the top of the part. We'll mesh the part, and I may want to increase the density of that mesh, so I'll go to my mesh settings, and I'm going to do 0.05, do 0.05 on this, and for the turn angle, let's do 30 degrees. And now I need to update that mesh. I'll then run my simulation. I'll turn off the visibility of the mesh view, and I'm going to decrease the exaggeration. So over here, remember, we can put it under actual displacement is from here to here, or we can exaggerate that so that we can see it better. And then for our displacement, we see about 0.17 inches of displacement, the same ballpark value that we had in Fusion 360. All right, I'm going to clone or copy this study. So I will do copy study, and then I will unexclude the split faces from the study, and then I'm going to replace those fixed constraints, and I'm going to do a frictionless constraint on this face. So this is sitting on top of the block wall, and I'll do a frictionless constraint on this face. I'll say okay to that. Now think of that constraint though is this piece can slide around in a plane on that block wall, that 8-inch area right in there, and we remove friction from the calculations. I'll then run the simulation. Okay, we get an error that states there are not enough constraints. Now sometimes, depending on how you set up the analysis, Inventor will automatically take care of the next step for us. In this case, it's asking we'll have to manually take care of that problem, but sometimes it will do it automatically. So what we'll do is we'll go to that analysis, and we will select Edit Study Properties. And then we want to set to detect and eliminate rigid body modes. Remember, when we see the word modes, think vibration or motion. We're doing a static analysis, and so we want to detect and eliminate any motion from this part. We'll say okay to that, and we'll run the simulation again. All right, this time we didn't get an error, and if we go to the displacement, we see that we have about 100,000 inch displacement with the beam sitting on top of the block wall. Now a question comes up all the time is, why did we get that error where the part could move when we have a perfectly symmetrical situation here where it's sitting on an 8-inch block wall here and sitting on an 8-inch block wall here? Why did we get that error? Well, remember, if we go back to the earlier lab where we were looking at the idea of this being a spider web, the spider can't build a perfect web from one end of this to the other end of this. So if there is any imperfection whatsoever, then that means our load isn't distributed evenly, in which case the part will go into motion. So what we did is we added a weak spring to this, a small force enough to keep it from moving, but not so much as to be significant in the analysis of the part itself. Let's copy this one more time. So now I'm going to clone this study, or copy this study. I'm going to delete the frictionless constraint on this end. If you go underneath a bridge, you'll see that most bridges are fixed on one end and then free to move on the other end so that they can expand and contract as temperature changes. So I have it fixed on this end and frictionless constraint on this end. We'll run that simulation again. We'll check the displacement on our latest analysis. Again, we see about 0.1 inches of displacement. Before I run this in SolidWorks, I want to make sure I have the same material properties. So I'll go to this material properties, and I'll select edit, and I want the mechanical and strength properties. And so I'm going to copy this to the clipboard, and then I'll have those values to use in SolidWorks. In SolidWorks, I'm going to start a new sketch on the front plane, and I'll draw a line over horizontally, and I'll dimension that line a distance of 480 inches or 40 feet. I'll then go to the weldments tab. Now if you don't see this, you may need to right click on one of these gray tabs and make sure you have the weldments tab loaded. And then I want to put a structural member in, so I'll do a structural member, and I'm going to go to ANSI inch as the file type. Now I've loaded additional library of structural member profiles. If you haven't loaded this library, you could use the step file from Inventor. I'm going to do a W section, and I'll do a W10 by 100, and I'll select this line and say OK to that. Alright, so now I have my beam in SolidWorks. I'll hide the sketch. Alright, so let's do this as Z pointing up, so this will be the bottom of my part on this side. I want to create a material with the same properties that we used in Inventor and in Fusion 360. So I've created a custom library, and I will then right click on that library and create a new category, and I'm going to call this Autodesk Steel, and I will get some other steel, let's say like AISI 1020, and I'm going to copy that, and then I'll paste that into my new category, and then I will rename this, and so I'm going to call this Autodesk Steel. So I have the same properties for this material that I had in Inventor and in Fusion 360. I'll set my units to inch, pounds, seconds, and for my modulus of elasticity, or Young's modulus, I'll do 3046, 1, 2, 3, 4 zeros. That would be 3.046 times 10 to the 7 for my density. And because we're using gravity on this one, the density becomes more important. I'll do 0.284 pounds per cubic inch. For the yield strength, 3002, 30020. And for my tensile strength, 50040. Okay, so make sure then we have our material properties applied to the part. I'll then go to simulation and study. I'm going to do a static analysis, and I will right click on fixtures, and I'll do fixed geometry. It won't let us select just this edge because we made this as a structural member in the weldment. SolidWorks already automatically sees this to run the frame analysis with beam elements, but I want to treat it as a solid body with tetrahedral elements. So I'm going to expand this cut list, and I'm going to actually, let's copy this study first. So I'll copy the study, and we're doing static analysis, and then for the second study I'm going to expand the cut list, and I'll right click and select treat this as a solid body rather than as a beam element. I have a sketch that's visible there. To turn off the visibility of that sketch, if we click on this arrow and go to our profile sketch here, and we can click there to toggle off the visibility of that sketch. Alright, then I'm going to do a fixed constraint, so I'll do fixed, and I'm going to select only this edge right here, and I prefer to do these as two separate fixed constraints. We'll see why in a later lab. So I'll do fixed constraint again, and then we'll define gravity. So for gravity, I want gravity pointing down in a negative Z direction. Select this face and flip that direction, so gravity is now pointing down, and then I will run this simulation. I want to check the displacement, so I'll go to the displacement, and I want to see that in inch units, and so I'll double click on the color graph, and I'm going to set it to floating, leave it on 3 decimal places, and I'll set the units to inches. And instead of exaggerating that amount, I'm going to do a user defined amount, and so it's 280, let's say 25. I'll have to check that and see. So we could have maybe exaggerated that a bit more, but we see that we have the same displacement, about a 0.17 inch displacement. And I again prefer to change the background to white. If we're recording this in a lab report with a white background, you don't have to print out the background of your screen. Alright, copy this study, and we'll do a static analysis again, and this time I want to split the face again the way we did in Inventor and in Fusion 360. So So I'm going to go to my constraints and I'm going to do a roller slider, but I want to split that face, and so I'm going to create a sketch on this bottom face and I'll draw my rectangle. Now again, we see that our dimensions aren't available, so we'll go back in and put that in a minute. So say OK to that, and then I'll exit the sketch, and I want to split that face. It's already selected, so I'll say OK to that. And I want to do a roller slider on this face, and I prefer to do these as two separate constraints. So I'll do the first one and then I'll do a roller slider on the second one. I'm going to delete the fixed constraints that we had from the previous study, and then I want to set that split distance to be 8 inches. And so I'm going to edit this sketch. I need to expand the split line. I'll edit that sketch and I'll dimension from this end, and that is 8 inches. And I'll do the same thing to the other end. From here to this end is 8 inches. I don't need to see these work planes, so I could turn them off over here, or I could come over here, turn off all my visibility of the work planes. And then I like to change the appearance of these faces. So I'll go to the appearance of that face and I'm going to pick some neutral color. Let's do the same thing on this end. Okay, so I have gravity. I have this beam just sitting on an 8-inch block wall here and here. I will run my analysis. Okay, just like in Inventor, we get a warning or error that the model may be unstable, and so we need to add a weak spring to the model so that we have stability. Now sometimes rather than getting an error, it might actually run and you will see an excessive displacement. In this case, it gave us an error. Let's go to the properties of the study and let's select this box right here to use soft spring to stabilize the model, and then we'll run the simulation again. Go to our displacement. I want to see it in inch units, so I'll double click on the color graph and I'm going to set to floating 3 decimal places, and I want to see in inches, and I want to reduce the exaggeration, so I'm going to do, let's do that as 100. Okay, so we see the exaggeration and we see our displacement about 100 thousandths of an inch. So same ballpark that we had in Inventor. We'll copy this study, and this time I'm going to put the fixed constraint on one end and the rolling slider on the other end. So I have the roller slider on this end. I'm going to leave that one on there. I'll delete this one and I'll do a fixed constraint on this end, and I'll run this simulation again. We'll go to our displacement and see about 100 thousandths of an inch displacement, same ballpark that we had in Inventor.